So today we're going to do session STG323, and it's building and optimizing a data lake on Amazon S3. I'm Brian Lyles, a senior principal engineer at AWS, and I'm joined today by Carl Summers, who is also a principal engineer at AWS. So, trying to understand the best way to convey how to do a data lake to people. You know, how do we make this a compelling story, an interesting story? So what we decided to do was to create a fictional company called Forever E-commerce. And what this talk is about is Forever's journey to having and running and maintaining a data lake. So to get started, Forever's primary goal is to sell widgets. Widgets are all the rage in 2024, but they found some success. And they've been collecting more and more data, as most of you, or a lot of you have. Now, this data is, some of it's structured, sits in databases, but some of it is not. It's just random data, unstructured data, images, not sounds, just random text. But also, what they want to do is they store it in multiple places. So some of it's stored in databases, some of it's stored in file systems, some of it's stored in S3. So the amount of data they have, amount of data they accumulate by the number of destinations complicates things and causes challenges, and it really slowed down their business. So what we want to do is talk about Forever E-commerce's journey, and to make this easier to follow, because we actually do have a lot of information in this talk, we've broken the talk down into 6 phases, 6 sections. The first is the realization, and to solve a problem, the first thing you need to realize is, hey, we have a problem here. So we'll talk about that. And then the next thing is well, we need to create a resilient architecture around our data lake. So what does that look like? And because you have all this data that could be PII, security-related data, or just data that you consider confidential or sensitive, we need to think about data security and governance. You can't have everybody reading all the data. And now, with all that data, so in phase 4, you're going to want to be able to retrieve that data. And whenever you build a data lake on S3, there's certain things that you might want to think about so that you can optimize those queries to get that data out as fast and as easy as possible. And then, when you have a large amount of data, you're going to want to think about the management of that data. It's like you have data from your e-commerce group or your operations group or from your data science group that has been created through transformations. How do we actually manage that? And then finally, we want to think about preparing for growth. There's one thing to say, and maybe some of you all have done this, where you've done all this work and you created a data lake and you went to your manager and you said, I did it. And then the next week comes, or your next busy season comes, and you realize that, oh, I did it, and now I did it to myself. So we need to talk about preparing for sustainable growth. So, like I said before, phase 1, the realization. So Forever E-commerce is powered on AWS. You know, they sell widgets online. And as the saying goes, like I keep on saying, you have to acknowledge a problem before solving it. And so we're going to have some characters in this presentation. And the first is Marcus Preston. He's the CIO of Forever E-commerce. And what he's talking about is the challenge of managing huge data growth while still delivering the reliable insights. The goal really is very simple: data confidence. Marcus has a counterpart, and this is Eugene Tate. And Eugene Tate's the CDO. And really, you know, I don't know if any of you all have been a CDO or not. He says to his team, you know, just store all the data in S3. Job done. And that's the end of our talk. All right. So like I said, it did not go that way. So like I said, we can talk about a whole bunch of things, but I wanted to break this talk down into 2 smaller sections. So really we're going to talk about 2 things. We're going to talk about collecting orders, and we're going to talk about streaming web clicks. And those are 2 different types of data that you might store in your data lake. And so first we have a web application, and that web application People make orders, and there's data that comes from the orders, the transaction, all the details, who bought it, where we're sending it to. And what we do is we take that, and it comes from all of our web servers, and we just periodically bulk upload that. Instead of writing it to, we do write it to a transactional database, but we also just take all that information and maybe we dump it out of our database and we periodically upload it to S3. But then we also have the clickstream data. And this clickstream data is coming in real time. Someone's clicking on your website and they're looking for things and they're going back, they're going forward, they're putting things in their cart, they're removing things from their cart. So this is a different type of data. This data is coming in real time, and the way that it works is we're using Amazon Managed Streaming Kafka, or MSK, as we're going to talk about it in the rest of this talk. And then we have Amazon Data Firehose, and it just goes right to S3 as well. And then you have, for the simplicity here, you have some data scientists who really want to know how things are going on, or what things are going on. So what they do is they do queries, and we're just going to say they use Amazon Athena. Now in this talk, I'm actually going to go over a lot of different topics that could have a lot of different services, but we're going to put that in a little bit of a ball, and we're just going to pick a certain number of services. And we're going to say this is not the only way to build a data lake, but we're going to give you things, if you're using Athena or you're using MSK or you're using some other things that we'll talk about, this is how you should cover it. So, there's always going to be some ops person who actually is the real hero of this story. And what they said is, well, with all this new data coming in, like all the orders and the click streams, we kind of ran into some problems. So let's talk about the problems that we're going to cover in this talk. The first one is that queries across multiple days or weeks worth of data take too long to process. I'm sure some of you all have ran into this. Another one is that there are concerns about sensitive data being too widely accessible. For instance, the data science team can view customer information while our country-based operation team should only have data for their country. Another thing is data lake in S3. Well, I can't find anything. It's becoming a challenge to locate specific data. For example, our finance team can't find any information about the orders that were shipped last month. And here's an important one. Well, you know, as we are throwing more things into the database and we are querying them in more ways and we are trying to bring more people into the fold, guess what? The costs are going up. How can we actually think about this? So, how do we approach this? Well, the first thing is, I'm going to break this down into 3 different ways. We're going to think about data layering. We're going to think about how to process your data, or how to bring your data into your data lake. We're going to talk about the raw data, the processed data, the curated layers, and what that actually means. And then we're going to talk about, well, how do I make S3 scream? And we're going to talk about that by saying that we're going to partition our data to make it very quick to retrieve. And then we're going to talk about my favorite topic, which is security and governance. I need to know who's using my data. I need to know what they're using it for. I need to know who let them use that data. So I'm going to bring up Carl, and he's going to dive into some of the topics.
The first problem Forever tackled was rethinking their data architecture. In this section, we're going to review how to think about storing data in S3. Here we're showing a 50,000-foot view of kind of our recommended mental model of structuring data in an S3 data lake. In essence, we're thinking about our data moving through 3 layers or stages, this raw, processed, and finally curated stage. In each of these stages, the data is going to be cleaned, potentially augmented. It'll gain more structure in terms of both its physical layout, but also its schematization. We're going to talk about some of the best practices for storing these stages in S3, how to think about the purposes these stages serve, and key considerations for building a resilient and scalable data lake in S3. So to ground this in something concrete, we're going to talk about the journey of our clickstream data in this data lake. Like we mentioned, the clickstream data is coming from an MSK cluster, and it's landing in batches of JSON line files. We're going to ETL that into a set of tables in Parquet format. Perhaps one of these tables is organized by session, maybe another by product line, another by customer segment, et cetera. And it's at this point that we may join that clickstream data with other data like customer history or augment it in other ways. And finally, we're going to load portions of that data into these curated data sets that are going to provide that historical performance metrics, maybe by marketing channel or customer segment. Now, of course, our data lake starts by collecting the raw data in S3. We should think of this data as the direct output from the business operations, so things like our clickstream data. But it's also going to be things like our chat logs from customer support, order state change data coming from our warehouses, and logs from our application servers, et cetera. Now, our clickstream data is being fed from our streaming platform, MSK, and so in this case, it is naturally ordered by time. So a reasonable key structure for it to land in S3 is something that looks like this, and it's segmented by date, for instance, year, month, day, and then finally a session ID. Now, general purpose Amazon S3 buckets automatically scale to very high request rates. But it's important to remember that they don't have this notion of directories, and instead have a flat namespace. Each prefix in that namespace can support up to 3,500 TPS of puts or 5,500 TPS of gets, and a bucket can have an unlimited number of these prefixes. This default scale means that for most workloads, we don't have to think about it too hard. But data lake ingest especially can be bursty, and new query patterns can drive unpredictable traffic to our data lake. For example, you may have a marketing launch that results in an increase of traffic to your websites, and along with that, you'll have a corresponding increase from your analysts in understanding the customer behavior during that time. With the proposed key structure, the top of every hour is going to see new traffic. Now, eventually S3 will identify that the traffic has moved to that new prefix and adjust the scale underneath, but in the meantime, your applications or your ingest may experience 503s, slowdowns, until that adjustment happens. And importantly, it'll see it at the top of every hour. So as we change from the 12th to the 13th, the 13th to the 14th, et cetera. So for high volume applications or high volume ingest, where we're exceeding this aggregate 3,500 TPS of puts or the 5,500 TPS of reads, we're going to want to adjust this key structure a little bit so that the heat can be spread across multiple prefixes and thus nodes. So in our example, we notice that this session ID naturally has some amount of randomness associated with it already. So we're just going to take that session ID and move it further up or to the left in the key space, leaving the rest of the structure intact. This is going to give Amazon S3 the opportunity to spread that traffic across multiple nodes, increasing the available RPS that your applications have. You may notice, however, that this makes new data harder to discover, as each possible session ID folder has to be explored or listed to identify if new traffic has landed for that day. We'll talk a little bit later about how a tool like Iceberg can help solve this problem. Now, our raw data is almost by definition highly or at least only partially structured. Your clickstream data is coming in as JSON files with probably a reasonable schema, but your chat logs with customer support are free-form text. You may even have direct uploads of imagery or documents by your customers. And tools like AWS Glue crawlers can be useful to automatically extract schema information from data, but also to be able to detect when new data has entered your data lake and it's ready for the next step in its journey into this processed layer. It's going to be at this stage that our data is gaining most of its structure. We're going to be doing things like cleaning it up, removing duplicates, fixing inaccurate or incomplete entries, and we're going to apply schema to the data to make it easy to understand and query for consumers. Importantly, most of our exploratory analyses happen on data at this stage. So we're going to make sure to organize it efficiently around core elements of its structure to make queries fast and cheaper to run. We'll also be making sometimes quite difficult decisions about what data needs to come along, but also what data we may have to drop. Now, two of the most critical decisions we make during this process are your data formats and your layouts. As a file format, Parquet is almost always the right default choice, as it enables great compression and allows for many types of query optimizations to occur. However, there are edge cases in this. For instance, if you know that your consumers of this data are going to want every column, a row-oriented format like Avro might be more appropriate. So in addition to the file format, we also have to make a choice in what we call a table format. In this key structure displayed, we have a typical legacy or a Hive formatted table, where things like our partitions are represented by folders in our key structure. Now, structuring our data this way allows for query engines to be able to exclude entire portions of the data if they know it's not necessary to satisfy the query. And this type of table format can get us a long way, but it was designed for a file system that offered various capabilities or invariants that are not available in Amazon S3 general purpose buckets. For instance, atomic folder renames. Additionally, because readers must use things like list to identify the contents of a table, they may see partial or in-flight writes. Failed writes may pollute your table with data that also leads to data inconsistencies. And finally, queries to your popular partitions can drive heat to specific S3 prefixes, which can lead to slow or even failed queries. The iceberg table format decouples the file layout from the contents and the organization of the table. So instead of using directories, the table structure is held in a set of metadata files that catalog and point to data files according to the partition and snapshot membership. When writing to an iceberg table, you should also enable object storage writes in order to inject a little bit of randomness into the key structure, which will allow S3 to scale to any read or write volume for the table. Iceberg's commit protocols also prevent partial or failed writes from being visible to your consumers, and allows for advanced features like time travel and rollbacks. And it also allows for write-efficient row-level updates and deletes that can defer the cost of the data writing into the query time. And we'll also talk about some mechanisms to pay that cost down as it comes. This decoupling of data from storage location means we have a great deal more flexibility to evolve the table structure as the needs of our analysts and our business change. Now, of course, adopting Iceberg doesn't come without trade-offs. Among others, while failed writes don't lead to inconsistencies in the table state, they do leave data files in our bucket. We'll need to clean those up. And it's also important to understand that doing a delete from the table doesn't necessarily remove data. It simply creates a new snapshot without that data available. And so we'll need to expire our snapshots as appropriate to make sure we clean up that data. It's very important that data in this stage be easy to access, understand, manage, and evolve. And a major part of that is registering your tables in a data catalog. The AWS Glue data catalog can be used to store the table definitions, where it's easily accessed in a multitude of places, including the analyst notebooks, their EMR jobs, their Athena queries, and elsewhere. Now, the tables and entities in this stage don't need to be direct corollaries of the raw input data. In many cases, there are joins or other transformations that make sense to do in this layer if they feed into multiple outputs in the next stage, which is where we're going to be deriving these curated data sets. Now, these tables and data sets are usually highly tailored to answer specific questions to your business. They must be well documented and easy to use. They're usually quite aggregated in order to provide that historical view over time. Most often, these tables are loaded into something like a data warehouse, like Redshift, to enable ease of access and performant queries. But they can also be stored in S3, where they're subject to many of the same considerations as we saw in the process layer. Just like our process tables, these tables need to be registered in our catalog to be visible to our consumers. Our consumers at this layer will also be very interested in things like the data quality. In other words, are columns containing only the correct values? Do we have the expected number of row counts? And they'll also be interested in the data's lineage. And tools like Apache Spline can interact with your various compute platforms to provide this lineage data. So the key takeaways from this section are that mental model for structuring our data in this data lake. It's raw, processed, curated forms. Choosing the right file structure and table structure, and planning our use of S3 to enable high performance and scale. By doing all of this, we're going to provide a solid foundation for maturing our data lake through security and governance.
Okay, so I was sitting there realizing that every part of this talk is my favorite part of the talk. So this is my favorite part of the talk. And we have Sheila, and Sheila Vivian is the CISO at Forever E-commerce. And what she was thinking is, well, with the resilient data architecture in place, Forever Now needs to focus on security and governance. In this section, we'll explore the essential elements for securing and governing our data platform. So let's dive into this. So when we think about security and governance for our data platform, I want you to think about 3 services. Actually, I'm going to teach you to think about 3 services first, and then you'll build your knowledge from there on all the things that you can use. But I want to talk about these 3 that are the core of thinking about security. The first one is AWS Glue Data Catalog. And what Glue Data Catalog is, to distill it down, is it knows about your tables, their schema, and the metadata in them. And then we have AWS Lake Formation. And what Lake Formation does is it allows us to build up ontologies of what people can see. And we'll talk about that in a second. And then we also have another product. And this product is Data Zone. And what Data Zone is, if you think about Glue Data Catalog as more of the technical bits, Data Zone is more about the people bits. I have data, and I want to share it with someone else in a secure way, and I only want them to see these things. And as an administrator, I don't want to deal with any of it. Because now what we can do is allow these groups to manage and share their data how they need. So I like terms. And one term that I do like is this term called a data mesh. So think of a data in a mesh form. And a mesh, like my fingers here, are all put together. But a data mesh is really a modern way to organize data that decentralizes ownership, making it easier for your organizations to handle large-scale data. Instead of having a single team, that one team that is the data team that actually does all the management of your data, what we can now do is give the data ownership to the actual owners of the data. And this is great as you start small and you scale and go out larger and larger and larger. Now everybody owns their own data. So, when approaching a data mesh, though, it's important to think about a few foundational principles. And really what they are at its core, a data mesh shifts ownership to the domain, to the business, whether it's finance, operations, or marketing, or whatever. By treating the data within each domain as its own data product, the teams who best know the data will know best how to share that data. So what we're trying to do here is introduce this title of this term as data as a product, where every team who owns their data and they view their data, they actually package it up in a product with the assistance of Data Zone, and then they can actually say who can access it, how you can use it, how long you can use it, and we can actually determine what you're using it for. So this mindset will make data more accessible and useful across the organization. And then really when it comes down to, I don't know how many of you work in highly regulated environments, this allows you to actually apply governance to your data in a way where it takes all the onus off of the bits of managing governance, but it actually gives you a plan and a mechanism which you can actually easily manage data in the small and at scale. So next I want to talk about lake formation as one of our other tools in this space. And what lake formation is we need to understand that we have data, and generally the data is in rows. We can think that way. And we want to make sure that people have access to the right data. So I have a couple examples here of what that actually means. So the first example is we have a team, the operations team that's in France. And due to GDPR and other things that we might be beholden to internally and externally, we only want the French operations team to be able to see things that happen in France. So instead of telling them to tack a and country equals France in all their SQL queries, what we can do actually upstream is just make it so that whenever they're looking at order data, that because of lake formation and the way we configured lake formation, that they can only see that. They can never see anything outside of that. And for them, that's all that exists. The next way that we can actually provide fine-grained access controls for data is to have columnar data. And what does this mean? Well, it means that sometimes not everyone should have access to every column in the data. And so in this example, what we have here is that our data science team, they shouldn't have to know anyone's name or anything identifying those people. So what we can do is we can use lake formation to provide a columnar filter that actually just removes that column from the data. No one can query it. And one of the neat things you can do is you can actually combine lake formation to do column and row, so you really can have fine-grained access to your data. The next thing we want to think about is combining taking those filters and then assigning them to permissions. And really what we can do here is after we define the row or the row level filters, we can actually say what people can do with the data. So in this example, if you notice the second line from the bottom, that this is a read-only role. The people who can actually access this data can only describe or select it. We could actually make it so they could update data as well, but in this case, because we don't want them to change order data, they can only describe and select. Another thing to think about here is, well, who can see what data? And what we can do here with AWS is that with our principles, you can use roles, you can use SAML, you can use, we have this idea of trusted identity propagation, which means that you can define within your Active Directory and your organization who has ownership to what. But the neat part here is that we've decoupled who can see it from how we define who those people are. So we have a data lake, and in our data lake, we have lots of data. But one of the problems with data lakes is that people like to throw things into lakes. So if I can't find anything in the data lake, how useful is it? So now what we want to do is talk about the actual governance of this data. So first thing we're going to do is we're going to talk about this tool or this service called Data Zone. And what Data Zone allows you to do is it allows you to define a domain for your data, and this domain could be your company or a business unit inside of your company. And then inside of the domain, you're going to have multiple catalogs. And this is important. I don't know how many of you all saw the keynotes over the past 2 days, but yesterday Matt Garman talked about Amazon SageMaker Studio. And one of the big things in Studio is that it has access to all your data. This is the way that you would actually create this access for your data, that you could define this catalog, and then inside of these catalogs you could have projects, and then you can assign those, do queries with the data, or do whatever else you need to do with the data. The neat part about this is that with Data Zone, what it does, it allows the streamlining of the data management within the central catalog, and then it allows for data in S3 or Redshift to be owned or to be managed, and the downstream folks do not actually have to think about any of this. So Data Zone also offers several powerful features that make data management easier and more efficient. One of it is, like I was saying before, is the data cataloging. But another thing that we have is access management. It allows us to set up policies to say who can share and controlling access across multiple accounts. This is not even in a singular account. Data Zone also allows you to have data quality and lineage tracking, so we can actually say if this data is correct and where the data came from. Finally, with lake formation, as I was talking before, we can apply these filters to make sure that only a certain segment of our population is allowed to see or access data. So I wanted to call out data lineage because I actually think it's a pretty neat feature, is that let's assume that you have data that's in an Amazon QuickSight sales dashboard, and you're sitting in your executive boardroom and you're going over these numbers, and someone from the back of the room says, wait a second, where did that come from? And generally what will happen is some data engineer or some data scientist or some poor dev will come and try to do the query to figure out where this data come from, and we'll look in logs and we'll try to determine that. Well, if you're using Amazon to manage your data, or Amazon Data Zone to manage your data, well, we actually have that built in. As we move our data through the raw processed curated tracks that Carl was talking about earlier, we can actually tell you not only where the data came from, we can tell you why it ended up in that place. So now we can go from an Amazon QuickSight dashboard all the way to the raw orders bucket and the clickstream bucket that it came from. So now let's talk a little bit about security around Data Zone. Or actually, just not security, let's just talk about Data Zone best practices. The first is tag your data so people can find it and give it useful information so people can find it. Use the fine-grained access controls through lake formation, but also monitor the data usage. Who is using your data? And then think about how can we build automation to how we can keep this data automated in the future. So, rounding up this section, just two more things here. One is your data lake, even though we call it a data lake, is not one thing. When you're building a data lake, think multiple accounts, multiple S3 buckets. And there's two reasons why. The one reason is someone is going to delete something. Oh, I deleted this bucket. Oh, okay. Well, now you deleted all my data. Well, if you've segmented this, you haven't lost all your data. The next thing is thinking about security. If you have multiple perimeters and you have a strong perimeter, if someone gets into one account, they can't get into all your accounts. And because we have IAM and we can actually do multi-account things here, it'll all work together. So, this goes without saying, but I have to say it, is we always store our data encrypted. We always move it encrypted. Last year, S3 encrypts everything, but I still want to make sure people who are not thinking about this is that you must encrypt your data at rest, and you can either use S3 provided, or you could provide your own keys. Or if you're in other cases, you can use dual layer protection. So the takeaways from this section are this. Set up fine-grained access controls. Use cross-account sharing to separate. Establish your data governance and discovery so people can find and use this data. Encrypt all the data. And then also design a security model that's flexible and ready to scale as you grow.
So now that Forever has tackled their data governance issues, they can start looking at how to make their queries run faster. Now, of course, query optimization is something of a dark art, and like all of the topics that we're trying to discuss today, we could actually talk for hours about it. Coming from a storage perspective, however, there's a number of really impactful and often easy to achieve improvements that you can make, oftentimes invisible to your consumers. So when talking through that process layer of data, we briefly touched on partitioning. Now, partitions, again, allow query engines to discard entire portions or chunks of data, usually very inexpensively. In this example, the query is looking for data for a specific date. And if our data is partitioned by that field, engines like Spark and Athena can know that they only need to read data under this 2024, 1019 directory or folder to satisfy this query. It's important, though, to understand that this partitioning has a direct effect on the data layout in the storage layer. In addition, partitioning by columns with high cardinality can also lead to very small data files, which can significantly reduce your query effectiveness, unless the queries that you run are very selective. In legacy tables formats, these partitions are expressed both as explicit columns in the table itself and by the directory structure in the underlying storage layer. And this has two knock-on effects. The first is that altering how data is partitioned requires rewriting all of the data in the table to adhere to that new partitioning strategy. And the second is that query writers, folks who are often not data engineers, must be aware of the specific partitioning strategies and write their queries to take advantage, often in very non-intuitive ways. So in this example, it's natural for a clickstream entry to have an event timestamp. But in order to partition these events, we have to decompose that timestamp into multiple columns, one for the year, the month, and the day. And query writers have to remember that they can't use just the event time column to query efficiently. They also instead have to manually convert that timestamp into those independent columns. The iceberg table format can help with both of these problems. Since data's membership in a partition is determined by the table metadata and not its physical layout or location in the storage layer, partitions can be changed for new data without having to rewrite the entire table. For example, it might turn out that our analysts tend to do a lot of queries on subsegments or specific segments of our customer base. Partitioning our data by this property can vastly improve the performance of those queries, but in a legacy table format, we would have to rewrite that entire table. In Iceberg, we can evolve our partitioning scheme, and as new data is written into, and importantly, as old data is aged out of the table, our analyst queries will just simply start to improve. Secondly, Iceberg supports a feature called hidden partitioning, where our partition values can be determined by transformations on natural columns. In our example, the data here can be partitioned by the day, month, or year of the event time, but importantly, our query writers don't have to manually convert this or adjust their queries to align with those partitions, and instead can express their queries in terms of the natural columns. And this makes it much more likely that they'll write both correct queries that also perform very well. Now, data within a partition is generally written out to multiple files, and when using a format like Parquet, metadata, like the minimum and maximum values of a column, can be found in the footer of these files. And when data is sorted by commonly queried columns, engines can often disregard sections or even entire files if they know that the value that they're looking for can't exist in that file. Iceberg helps here as well by elevating much of that information up into the table metadata so that engines don't even have to look at the data files themselves. Notably, linear sorting on multiple dimensions, though, has diminishing returns, and it requires often that queries have predicates on the elements of the sort hierarchy in order to benefit from the sorts on fields lower in that sort hierarchy. I'm not going to talk about the details, but I do want you to be aware of an algorithm called z-order sorting that can be very useful and have great benefits when your data has natural clustering across multiple dimensions, and your readers have widely varying query requirements. Now, compressing our data is a somewhat obvious choice. If the data is smaller, it's faster to read, and my queries perform better. Many writers like Spark compress their output by default, which is great. What might not be so obvious, though, is that the difference in size and speed that the different compression algorithms can bring. The effectiveness of compression is often very data dependent, and it's going to require a little bit of experimentation on your part. However, for our internal data lakes, we're seeing an average of 5 to 6% storage reduction for the same CPU time and cost when using Z standard, even at level 9. And the best part of this change was that support for Z standard is pretty universal at this point. So the development effort in many cases was configuration change. Now, part of getting good compression is making sure that there is sufficient data in your windows to compress over. We see the best performance with the setting called a data page size of roughly 1 MB. Of course, it can be hard to drive that, and it's going to be dependent on your data, but it often requires row group sizes of roughly 128 MB. Notably, we see diminishing returns after that, though. Now, usually we want to sort our data to improve our query performance. But if there aren't obvious fields that benefit from this, or we just don't know, sorting can still vastly improve the effectiveness of our compression. We've run some experiments on our internal data lakes where we took every pairwise combination of 2 fields in our tables, and we sorted the data by that pair. And the most efficient pair in some of these examples came out as much as 22% better than the natural sort order of the data as it arrived in the data lake. Of course, sorting isn't free, so if you're not going to get query benefits from it, you'll only want to pay this cost if the data is going to hang around for a long time. Now, I've mentioned Iceberg a handful of times throughout this section. I'm quite a big fan. And I don't have time, though, to go into significant depth about the remaining features. But for us, Iceberg's core advantage is in the ACID guarantees you get, the efficiencies it can help drive when querying petabyte scale tables, and the ability to evolve both the partitioning and the schema as our needs change. In the context of performance improvements, though, I do want to talk briefly about the compaction feature of Iceberg. So as I mentioned, small data files can lead to inefficiencies in querying, as opening those files incurs a certain amount of overhead. The effect of this overhead obviously increases as the average file size decreases. So one method of mitigating this overhead is to collect multiple of those small files and rewrite them into a single large file. And Iceberg exposes a stored procedure called rewrite data files that does exactly that. It's also a great opportunity to modify the sort order, including using that z-order sort. However, these compaction workflows result in new snapshots of the table, and thus they can compete with other write workloads to the table. And thus for very large tables, we recommend, or tables rather with high write volumes, we suggest compacting on a partition by partition basis, and also enabling the partial progress feature to reduce the likelihood and impact of conflicting commits. Yesterday, S3 announced the general availability of S3 tables, which is a fully managed solution for Apache Iceberg tables in S3. Table buckets bring a number of benefits, including faster query performance out of the box due to tuning in the storage layer. They also bring improvements and simplifications for security, as tables are now rather than just a collection of objects in a bucket, they are now a first-class citizen. Additionally, many of those management features that I talked about, or management responsibilities rather, can be delegated to S3 and controlled via configuration, simplifying most of our lives. All right. Also don't have time to go into all the multitude of query engines and how to optimize them. So scoping this down to just Athena. As many of you know, Athena is a managed service for both the Trino and the Spark engines. And it provides a number of useful tools that you can find at that link for performance engineering, especially in the context of your more complicated joins. I want to call out that when you're using Athena, be sure that you're making use of the work groups to provide resource utilization isolation between your users. And also use cost allocation and CloudWatch metrics to monitor and control your costs. Athena also logs its usage in CloudTrail, which can be a useful mechanism for identifying who's accessing your data and, importantly, where they are writing their results to. Now, optimizing queries happens both in your micro and in your macro choices. We've talked about the benefits that Iceberg can bring, but you should also be thinking about looking to apply the right compute platforms for your queries. We've talked about Athena, but for instance, Redshift is really well suited for performing complicated queries across multiple different data sets. And with technologies like Spectrum and its integration with S3 tables, continues to allow you to choose the right storage technology. So the key takeaways that I want you to bring away from this section are to select your efficient data formats, partitioning strategies, and your sort orders. Experiment with them. Find out the ones that work best for your data. Monitor your users to identify their common queries, and then evolve your partitioning strategies or your sort strategies to adjust. Consider adopting an open table format like Iceberg to make many of these performance benefits and improvements easier to achieve and invisible to consumers. And that was it, sorry. All right. I think I'm still up.
Oh, yeah.
Yeah. All right. So with their data lake performance optimized, Forever One now looks to improve their data quality and control their storage costs. So we're going to talk about two big levers for measuring and managing the quality of our data, and some other core S3 features that make it simple to manage costs as the size of our data lakes grow. Of course, the quality of our decisions is determined by the quality of our data. As data is moving between these raw, processed, and curated layers, we want to make sure that we're monitoring, alarming, and fixing issues as we find them. Glue data catalog can be used to validate both the correctness of our data. Things like, do columns have expected values? And are those values within expected bounds, etc. And it can also be used to monitor the completeness of our data. Are there columns with missing values, or is there a mismatch in the expected row count between one of these layers and the other? Metrics and events, based on the result of evaluating these rules, are published to CloudWatch Metrics and EventBridge, where we can set up automation and alarms to notify us of bad data or to trigger workflows to go correct it. Iceberg also supports something like a Git-style commit log, which allows for features like tags and branches. And importantly for your data quality, it enables a workflow called the write, audit, publish workflow. New writes into one of our processed or curated tables are done to a staging branch. After the writes are complete, we can run our data quality analysis or our audits, including manual verification if we want to. And once that we're satisfied with the quality of this new table or the data within it, we can fast forward it onto the main line of the primary of the table, making it visible to standard consumers. And importantly, this workflow can be extended to multiple tables where we're doing cross-table validations. Once we're happy with the state of all of our tables, we can fast forward them and then tag them so that consumers know which versions can be used together. Now, at all stages in our data's journey, S3 offers options for cost-efficient storage with trade-offs on access time and cost, and choosing among them generally requires understanding your data access patterns. As an example, our raw data is likely accessed numerous times immediately after landing in S3, and then probably not very often after that. However, keeping this data around for long periods of time can be useful either to meet compliance requirements or to be able to extract new insights as our understanding of our business or our business needs evolve. In this case, you'll probably want to land that data in S3 standard and then transition it after a few months or weeks to an archive tier, perhaps Amazon S3 Glacier Deep Archive, for inexpensive long-term retention. Our process data sets, however, are likely to have an unknown or changing access patterns because our data scientists are constantly evolving their analyses or they're reacting to urgent business needs. And in this case, S3 intelligent tiering probably makes the most sense as it will automatically move data to the most cost-efficient storage tier based on the access frequency. So at a very high level, when you understand your access patterns very well, use explicit lifecycle policies to transition data between the storage classes. In all other cases, recommend that you simply land your data directly into S3 intelligent tiering. So in this section, we talked about some key strategies for ensuring a high bar for data quality and how to control your storage costs through storage classes, including when to use S3 intelligent tiering. This time.
All right, so now we're in phase 6. And really what we need to think about is that we have a data lake, but how can we have a data lake for the long term? In this section, we will actually review some things about having a data lake for the long term. The first thing you want to do with your data lake is collect all the metrics. And when I say collect all the metrics, don't just think about S3. You need to think about if you're using Glue crawlers, Glue data quality, you need to collect metrics from that. If you're using EMR, you need to collect metrics from that, whether it's EKS, serverless, or EC2. But also if you're querying with Athena, query with that. And in this example, we were talking about MSK, so you need to collect metrics from every piece of all the services that contribute to your data lake. The next thing we want to do is you want to think about dashboards and alarms. You can't have metrics without having some way to notify if something is wrong or is going to be wrong soon. So you want to establish your KPIs, which is figuring out the important metrics, which I'll actually talk about in the next slide. You want to configure the alarms for what is critical for you. I wanted to give a list of what is critical, but it really depends on what your use case is. And then you might want to trigger your alerts through SNS, or you could use another service. So when we think about the key metrics, what we really want to think about are the high-level things. We want to make sure that our data is good and that it actually has valid data in there. We want to make sure that it is available and that not only is it available in a way that is performant so that our queries and our processing actually happens in a good amount of time. We want to think about storage and cost management. You want to understand where costs are going, and you don't want costs to be a surprise whenever you get the bill for your data lake. And then you want to think about security. Who has access to what? Who accessed what? Who gave that person access? You want to be able to monitor those as well. So when this deck was first created, this slide was actually horizontal, and there was 5 things under each one of these. And I got feedback that was like, Brian, that is too much text for one thing. And I said, yeah, I guess so. But I want you, if you're taking pictures, I actually do want you to capture this, is because whenever you're thinking about KPIs, because someone's like, just capture some KPIs, here is a good list to start from. And really, just think about storage, cost, and efficiency. Make sure you are storing and accessing data in a cost-effective way. Another one is like scalability. Monitor how fast data is coming in, and then how your analytics tools are scaling. If you're using EMR, how many new instance nodes are spinning up, or EKS, and you have new Kubernetes nodes spinning up? Figure out how fast that's happening. You need to know that. And then you want to think about data quality. Are we actually ingesting bad data constantly? Well, now we have something to fix. And then you want to think about, is it usable? Is there metadata in data zone for all the data that we have? And then finally, something else that you might want to think about is, I hope you all are using CloudTrail for the auditing, but here's something interesting that a lot of people don't think about. There's not as many as I thought, is that take all of your auditing data and then put that in your data lake. And now you can use the same tools to query the data that actually is about what you did in the same method that you're using for your business functions. Another thing we want to do is, growth is going to come. So really what we want to do is we want to take humans out of the loop. We want to have continuous monitoring and you can use CloudWatch to do that. We want auditing to make sure that we are secure and compliant. That's where we can use CloudTrail. We want to think about cost management. We want to make sure that we are not spending in ways that we are not ready for. And we also want to think that our data lake is this big now, but in the future it'll be this big. So we need to think about what scalability looks like. And like I said before, we need to take humans out of the loop. You're not going to have one person who's going to solve all these problems for you. We need to build automation around this. So we covered 6 phases, and I really want to just go over these. So with Forever e-commerce, they use these ideas to actually grow and mature their data lake. So if you were going to, what are the takeaways from this talk? The first one is establishing a scalable architecture using S3 as a foundation is a good start. The second is we want to implement data ingestion efficiently with services like Glue and streaming solutions. Next one is optimizing query performance and cost through partitioning, file formats, and sorting strategies. Next one is we want to make sure that we have secure access. We want to secure access by paying attention to how we implement our IAM. We're going to think about lake formation and what's actually going in and out of Glue Data Catalog. And then finally, and especially in the way that the world is right now due to regulations and things like that, we want to make sure that we're employing governance to ensure that we understand how data is being accessed. And finally, logging and auditing. You are only as good as the information that you can collect about how things are happening. So make sure that you are actually keeping that information for future usage. For usage you might not even know right now. So with that, I just want to say thank you. And if you have any questions, we're here to answer them.